Hi, everyone. My name is Hoifung Poon. I'm the Senior Director of Biomedical NLP in Microsoft Health Futures. Today, I'm very excited to be here to be giving this webinar with my colleague Jianfeng Gao, who is a distinguished scientist at Microsoft Research and also the partner research manager of the Deep Learning Group. Together, we are going to present to you our latest advances in domain-specific language model pretraining for biomedical natural language processing. So in the mainstream NLP, the focus has been on the general domains such as the newswire and the web. And in recent years, one of the most exciting advances is in the neural language model pretraining. And there has been actually an ongoing arm race in training error bigger models with error larger text corpora. Many benchmarks and leaderboard have been also created so that we can evaluate those language models and track the progress by the community. In biomedicine, on the other hand, the landscape is quite different. The biomedical texts such as PubMed papers are very different from the general domain ones. However, biomedical NLP has received relatively little attention in the mainstream NLP research. For example, the biomedical language models tend to be a simple extension of the general domain one, and there has been no existing leaderboard for biomedical NLP. So in this webinar, we are going to present to you a new paradigm that we have been pursuing to pre-train language model for specialized domains such as biomedicine. This has led us to produce the PubMedBERT, which has attained state-of-the-art result in a wide range of biomedical NLP tests. We will also present to you the BLURB, which is a comprehensive benchmark and also the first leaderboard for biomedical NLP. So in the first half of the talk, I will start by sort of motivating biomedical NLP and show how it can help revolutionize biomedicine. I will then contrast sort of the conventional paradigm for domain-specific training, which motivate our new paradigm for pre-training from scratch the specialized biomedical language model. I will also explain a little bit why we need a comprehensive benchmark and the rationale behind the BLURB. In the second half, Jianfeng will walk you through the practical side of the biomedical language model pretraining, including the PubMedBERT pretraining and our head-to-head comparison against other BERTs and also across many task-specific modeling choices. So as we mentioned earlier, biomedical NLP is quite different compared to the mainstream NLP, but it has been relatively underexplored in the past. However, it can actually potentially have play a very key role in the emerging area of precision medicine. So in the ideal world, we want every patient to be able to respond to the treatment they have been prescribed to, as signified by the blue person on the left of the graph here. In the real world, unfortunately, most of the patients do not respond to the treatment they have been prescribed, as signified by the red person here. So this is obviously a well-known problem for a long time, but in the past, the challenge is that we used not to have a lot of fine-grained feature to be able to distinguish the blue from the red a priori. So the advent of big data in medicine promised a change for the good, and cancer is the poster child for this. With the tumor genomic sequence, for example, we are literally staring at the source code for the cancer and can potentially distinguish individual patients down to the individual level. Another major disruption is the rapid digitization of the medical records, which provide us with fine-grained information of longitudinal patient trajectories. So all this are very exciting, but the big data also present a grand challenge of information overload. For example, the tumor genomic sequence doesn't buy us anything unless we can translate them and interpret them and actually turn them into actionable insight for treating the cancer patients. Currently, this has been done completely manually by the so-called molecular tumor board, which is obviously not scalable. A major bottleneck for tumor board is to be able to gather all those knowledge from the literature, such as the knowledge about the gene, the mutation, and how they predispose the tumor with respect to a drug treatment regimen. So all this information is gathered in the PubMed paper, which adds 4,000 new papers every day and over 1 million every year. And similarly, there has been a lot of fine-grained information, as we mentioned earlier, but they actually get buried underneath all those medical texts, such as the clinical notes. A cancer patient can easily have hundreds of notes, which can take hours to curate all those available information. So biomedical NLP can help by enable us to unlock those such knowledge from the biomedical text at scale, and thereby facilitating clinical trial and clinical care and research. From the literature, we can extract a PubMed scale knowledge graph where the notes are basically all these key medical entities such as a drug, gene, mutation, disease, and the edge or hyper edges are the relation among them, such as drug response or genetic regulations. And with all this information, we can accelerate progress in drug discovery, repurposing, as well as clinical decision support, such as in the molecular tumor board. From the medical records, one particularly exciting direction is to curate such a population-level real-world evidence, which capture the longitudinal information about the diagnosis, treatment, and outcome information for patients. And this information can enable us to facilitate and greatly accelerate clinical trial matching, post-market surveillance, as well as conducting things like virtual trial that can drastically reduce the cost for drug development. So hopefully I have convinced you that biomedical NLP can play a key role in helping to materialize the prospect of precision health and revolutionize biomedicine. However, there are many steep challenges for biomedical NLP. First of all, people tend to have used very different ways to say essentially the same thing. So here are just a few ways to state the simple fact that the tumor suppressor p53 can inhibit the apoptosis pathway BCL2. In a small corpus of a couple thousand abstracts, there is already an extremely long tail of words that can be used to signify such negative regulations. On the flip side, the same expression can also mean completely different things. So for example, there is a gene called PDF. So as you can imagine, a biomedical NLP system has to be able to disambiguate such gene reference from other meanings, such as like the text format or maybe some other acronym like probability density function. Now, obviously, variation and ambiguity are the bread and butter NLP challenges. But in biomedicine, there are also additional challenges that have been received relatively little attention in the mainstream NLP research. In biomedicine, the most valuable information tend to exhibit little redundancy, such as the latest medical findings. Such information is often expressed in very complex linguistic way. And if we are sort of like skipping some of those facts, they could literally mean life or death for some patients. So we have no choice but have to tackle such a complexity head-on so that we can leave no fact behind. For example, in most of the information extraction research, they tend to be focusing on binary relation within single sentences. In biomedicine, we tend to need to extract much more complex relation which can span across many sentences. For example, in the molecular tumor board, you might care about how would a tumor with certain gene and mutation would respond to a particular drug regimen. So such a ternary relation can easily span across many paragraphs, as you can see in the example here. In biomedicine, we also lose a very powerful tool, which is the crowdsourcing. So in mainstream NLP, it's a common practice to have mechanical Turkers to help produce a very large labeled data set, which can help train the NLP systems. In biomedicine or other specialized domain, the challenge is that the average Turker tend not to have the domain expertise to doing such an annotation task. For example, you can imagine asking an average Turker to interpret a cancer genetic paper for you, or interpret a CT scan. That would be pretty hard. Now, language model pretraining represents one very powerful approach to help alleviate such an annotation bottleneck. Unlike in the standard supervised paradigm where the label example become the bottleneck for the supervised training, in the so-called self-supervised learning paradigm, what the key insight is that we can leverage the abundantly available unlabeled text and then essentially hallucinate some noisy training data in those unlabeled texts at scale so that we can help bootstrap the learning. And neural language model represent a task-agnostic way to do this kind of self-supervised learning. Given the unlabeled text, essentially what we are going to do is to pick just a random subset of words to high, and then ask the language model to predict them back. So by doing so, we are forcing the language model to capture a lot of those semantic dependency in the text, and thereby they can produce sort of very meaningful features to enable very efficient learning for the downstream NLP task. So such a neural language model pretraining has attained a lot of success in the general domain. So for specialized domain like biomedicine, it's quite natural for folks to start focusing on, assuming that all this general domain language model is still quite helpful. And in fact, the standard mixed domain pretraining paradigm tend to essentially inherit the vocabulary from the general domain, starting from the generic language model before actually training with the in-domain text. So such a paradigm makes perfect sense if our target domain has very little text to use in pretraining, and thereby in this way we can actually leverage the transfer learning from the general domain text to help a particular sort of domain-specific pretraining. In the biomedicine, however, we observe that this rationale actually start to break down because we actually have plenty of the unlabeled text in the biomedical text. As we mentioned earlier, PubMed has over 30 million papers and add over 1 million every year. So this has motivated us to start looking at actually a new paradigm for pretraining language model for such a specialized domain. In which we actually conduct pretraining entirely using in-domain text. And for example, in this case, we will be actually conducting the pretraining with just the PubMed text, and we will call the resulting language model the PubMedBERT. To see why this paradigm can actually be advantageous, let's take a look at the vocabulary, which is a fixed size set of frequent words and subwords, on top of which where the language model tries to learn to acquire those meanings. So only a very few common biomedical terms occur frequently enough in the general domain so that they will be chosen into the vocabulary and be modeled as first-class citizens. So on the other hand, many of the other words, biomedical terms, will instead be shattered into sort of essentially fragments. And then during the in-domain training, the language model are forced to basically learn using such essentially meaningless fragments for the biomedical context. We should also keep in mind that during the in-domain training, pretraining, the language model actually also have to essentially unlearn a bunch of those irrelevant connotation from the general domain that have nothing to do with the biomedical domain. So this is partially why pretraining from scratch, as we are taken in the PubMedBERT approach, can potentially be much more superior to the mixed domain pretraining. And later in the talk, as you can see, this indeed results to significant performance gain in many downstream NLP tasks. Now, to facilitate this study, we have created BLURB, which is a comprehensive benchmark for biomedical NLP. In the past, there have been many data sets and shared tasks for biomeds. However, many of them tend to focus on individual tasks. A key advantage for language model pretraining is that it's essentially a universal way to help a wide range of downstream NLP tasks. It is therefore imperative to create a comprehensive benchmark so that we can evaluate across many biomedical NLP tasks. So recently, BLUE is an attempt to address this need. But the BLUE data set still have relatively little limited coverage for biomedical tasks. Most importantly, BLUE actually mixing up the PubMed-based biomedical tasks with the mimic-based clinical tasks. And as we can see later, these two domains, even though they are highly related, are still very, very different. So this has motivated us to create BLURB, which is short for Biomedical Language Understanding and Reasoning Benchmark. Our goal is to produce a comprehensive and domain-specific benchmark so that we can facilitate evaluation on the biomedical language model pretraining. As you can see, it consists of 13 data sets that's spanning 6 diverse tasks, which include name entity recognition, evidence-based medical information extraction, relation extraction, sentence similarity, document classification, and question answering. So compared to prior work on biomedical pretraining, the BLURB is the most comprehensive. So this concludes the first half of the talk, and I will pass on to Jianfeng, who will walk you through the practical side of biomedical language model pretraining.
Hello, I'm Jianfeng Gao from Microsoft Research. In the second part of the talk, I will present PubMedBERT, which is a domain-specific pre-trained language model for biomedical NLP. And we will also present some comparison results between PubMedBERT and other pre-trained models using the BERT benchmark. We are releasing the pre-trained models and the benchmark for the community to help accelerate the research. Let's see how the PubMedBERT model is trained. Unlike the widely used mixed domain pre-training approach, where a language model is often first pre-trained using general domain text, such as newswire and web text, and then continually pre-trained using target domain data. PubMedBERT is pre-trained using target domain data from scratch. The target domain data here are a collection of PubMed papers. Our method is motivated by a few considerations. First, mixed domain pre-training is a form of transfer learning, where the general domain data is assumed to be helpful for the applications in the target domain, because the target data is scarce, and the general domain is assumed to be relevant to the target domain. But this is not the case for the biomedicine domain, where the biomedical data or text is very different from general domain text, and we have large amounts of PubMed papers for domain-specific pre-training. We will show in a minute that the domain-specific pre-training from scratch substantially outperforms continual pre-training of generic language models, thus demonstrating that the prevailing assumption in support of mixed domain pre-training is not always applicable. Our domain-specific training takes 2 steps. First, we generate an in-domain vocabulary from PubMed papers. This vocabulary contains many common biomedical terms which are not included in the vocabulary used by most of the generic language models, as Hoifung showed in his part. Then we pretrain PubMedBERT using the standard mask language model objective. We mask a few words in the text and train the model to recover these words given the context. Now let's see how the model performs. In this table, we compare PubMedBERT against some of the existing state-of-the-art pretrained language models around 4 dimensions: vocabulary, pretraining methods, the domain, and the size of the training data. Well, we notice that BERT and the Robota are general domain language models, and the vocabulary in the models are learned from Wikidata, from book corpus and the web data. Robota is trained on much larger training data and is more robust than BERT across many NLP tasks. And the BERT, BioBERT, Clinical BERT, BLURB are all trained using mixed domain pretraining. They're initialized by BERT and then continually pretrained using biomedical text. Note that in the continual pretraining approach, the vocabulary is the same as the original BERT model, in this case, the one generated from Wikipedia and book corpus. While convenient, this is a major disadvantage of this approach, as the vocabulary is not representative of the target biomedical domain. SciBERT is a notable exception, as it generates the vocabulary and pretrains from scratch using biomedicine and computer science papers. However, from the perspective of biomedical applications, SciBERT still adopts the mixed domain pretraining approach because the computer science papers are clearly out of domain. The version of PubMedBERT we use for comparison use the training data that contains PubMed paper abstracts, which amounts to 3.1 billion words. We perform 2 types of comparison. First, we fix the task-specific modules for each downstream task and compare different pretrained language models. Second, we fix the pretrained language model and compare different task-specific model choices for each task. In both cases, we fine-tune the whole models. Here is the general architecture of fine-tuning a pretrained language model for downstream applications. First, an input instance is processed by a transform input module, which performs task-specific transformations, such as domain-defining entity mentions for relation detection. Then the transformed input is tokenized using the vocabulary and fed into the language model. Next, the contextual representation at the top layer is processed by a featureized module and then fed into the predict module to generate the final output for a given task. To compare language models, we fix all the task-specific modules as highlighted in this figure. Note that the architecture of the featureizer is fixed, but the parameters are updated together with the rest of the language model during fine-tuning. Now we compare all pretrained models by applying them to the downstream NLP tasks in BLURB. For each task, we conducted the same fine-tuning process using the standard task-specific models. We can see that by conducting domain-specific training from scratch, PubMedBERT consistently outperforms all the other BERT models in most bio-NLP tasks, often by a significant margin. The gains are most substantial against the BERT and the Robota models trained using general domain text. Most notably, while the pretraining corpus used by Robota is the largest, its performance on bio-NLP tasks is among the worst, similar to the original BERT model. And the models using medical text in pretraining generally perform better. However, the mixed out-domain data in pretraining generally leads to worse performance, in particular as evidenced by the results of clinical BERT and the BLURB. Even though the clinical notes are more relevant to the biomedical domain than general domain text, adding them does not introduce any improvement. Like PubMedBERT, SciBERT is also trained from scratch, but it uses mixed domain data for training, so it significantly underperforms PubMedBERT. Not surprisingly, BioBERT is the closest to PubMedBERT, as it also uses PubMed text for pretraining, but initialized using BERT. However, we see that by conducting domain-specific training from scratch, including using the PubMed vocabulary, PubMedBERT obtains consistent gains over BioBERT. We also tried adding full-text articles from PMC as pretraining data. The training data is much larger than the PubMed abstracts. Surprisingly, this leads to slightly performance decrease. There are several reasons. Since the full text contains more noise than abstract, and the most bio-NLP tasks are based on abstracts, so the full text may be slightly out-domain. Moreover, even if full texts are potentially helpful, additional pretraining cycles are needed. It turns out by extending pretraining for 60% longer, the overall results slightly outperform the standard PubMedBERT trained only on abstracts. And we leave it to future work to explore how to more effectively leverage full text data. Next, we study the effect of modeling choices in task-specific fine-tuning by fixing the underlying pretrained language model to our standard PubMedBERT. Prior to the success of pretrained language model, standard NLP approaches were dominated by sequential labeling models such as LSTM. With the use of the self-attention mechanism, the top layer in BERT already captures many nonlinear dependencies across the entire text span. Therefore, it's conceivable that even a simple linear layer on top can perform competitively. And we find that this is indeed the case for name entity recognition or NER and relation extraction tasks. As shown in this table, the use of bidirectional LSTM does not significantly outperform a linear layer. The use of neural methods also has subtle but significant implications for relation detection. Previously, relation detection was generally framed as a classification task with manually crafted feature templates. And to avoid overfitting, the templates typically avoid using any entities in question. Neural methods do not use handcrafted features, but use the neural encoding of the given text span, including the entities themselves. This thus introduces a potential risk that the neural models may simply memorize the entity combination. As a result, it is a common practice to dummify entities, for example, by replacing an entity with a generic tag. We thus conduct a systematic evaluation of entity dummification and relation encoding using relation extraction tasks as example. As shown in this table, simply using the original text is the worst due to overfitting. Dummification remains the most reliable method. Interestingly, using both the entity marks and dummification leads to slightly better results, as it appears to prevent overfitting while preserving useful entity information. We are releasing the pre-trained PubMedBERT models and the BERT benchmark to public. Our goal is to accelerate research on BioNLP by lowering the entry barriers, facilitate reproducibility, and tracking community progress. Given the importance of the BioNLP, we encourage researchers around the world to participate, starting by evaluating your models on the BERT benchmark. BERT actually is a collection of resources of conducting BioNLP research. We have created the first BioNLP leaderboard. Welcome to submit the results of your models or systems. And we also upload the pre-trained PubMedBERT models to the Hugging Face site. And the model has more than 1,000 downloads in the first week. Our future work includes further exploration of domain-specific training strategies, incorporating more tasks into biomedicine NLP, biomedical NLP, and extension of the BLURB benchmark to clinical and other high-value domains. Thank you.
Hi,
Hello?
everyone. Hi, everyone. This is Hoifung Poon, and welcome to the webinar. And Jianfeng, do you want to introduce yourself?
Yeah, this is Jianfeng Gao. Welcome to our talk. Now it's the live QA time. We receive a lot of great questions and try to answer all of them at least as much as we can. I would like Hoifung to already go through the questions and we jointly provide answers. Okay, Hoifung, just go ahead.
Yeah, sure. So there are a bunch of great questions, and we have answered a few in the chat. Let's see. One of the really good question is about that. Would it make sense to pre-train a model on a combination of multiple corpus? Like, and is it the main problem is computation costs, or does it depends on the target domain? I would say that computation cost is one factor, right? But if you don't care about computation costs and only care about performance, the real question is depends on your applications. If your application is all open-ended, like you don't know where your next instance come from, right? For example, you're doing open domain QA, you don't know whether the next question will be like in general domain or in medicine and so forth. In that case, it makes sense to train a more broad coverage language model so that you cover as much as possible. But if you know ahead of time your application is actually in a specific target domain, then in that case it could be beneficial to train that language model just for that target domain.
When you pick questions, can you also give me the number of the questions so I can follow it easily?
Yeah, so the question I just answered is like number 7.
Number 7. Yeah, that's good. Let's move on next.
Yeah, and then there is a question like, is the PubMedBERT portraying on data that's used in the PubMed QA task? So the PubMedBERT model is portraying on all the PubMed, and if that would actually include all the abstracts. So that would basically include definitely the text in the PubMed QA task. One thing to be clear is that the pretraining is only have access to the unlabeled text, so it doesn't actually have any label information, as pretty standard in the pretraining.
Question number 9 is also very interesting. It says that apart from the PubMed source, have you tried to utilize some biomedical specific knowledge graphs to enhance these BERTs? Do you think that will be helpful in biomedical domain NLP? So great question. We are thinking about along the same line, but at the moment, the PubMedBERT is trained without leveraging any knowledge graph. This is definitely our future work. And we already started trying to use the transformer to encode knowledge graph in a small scale and see pretty promising results. Yeah, definitely we're going to leverage the knowledge graph, because knowledge graph probably are more informational than pretext in some sense. So then the challenging research question is how we leverage both. Do we do curriculum learning or simply combine these data source? For example, we can generate text from the knowledge graph, then just combine the train data. Okay, yeah, it's a very good question. We hope we can get some results pretty soon. Okay, thank you.
Yeah, and then question number 11. Quantitative value also encoded in this model. The quantitative numbers are often very important for the medical case. This is a great question. Right now, we don't do any special encoding. So we simply treat it as just another, character stream. So it will be broken into subwords just like any other words. So there are definitely some domains and application where this kind of value actually get into very important. For example, one particular example that we have been noticed is in the pathology, right? For example, for cancer pathology report or radiology report, when they start to talk about, how big the tumor size is, right? What's the dimensions and so forth. Those are actually those numbers are directly related to, for example, whether the patient is on stage 2 or stage 3 and so forth. So in those cases, actually, the standard encoding is actually not doing a very good job. So it's actually for specific application, we have tried actually more specialized encoding, but in general, it's actually a great area to look at.
Yeah. Okay. The next question, 12, is about evaluation. When you say that PubMedBERT outperforms other methods, do you have any statistical analysis to support your statement? And yes, if you read the paper, whenever we mention that this result, this improvement is significant, that means we run some sort of significant test. But for many cases, since the evaluation data is pretty large, so and the improvement margin is big enough, so most of the improvements are statistically significant. Not by chance. Thank you.
Yeah, we also assess the the standard deviation, and exactly like Jianfeng said, like many of these data sets are actually big enough. Certainly, there are some exceptions, right? Like biosis, that's relatively small. But for most of them, actually, if you look at the standard deviation, and you can see that the gap is actually more than that.
Dr. Hoifung, you want to take the next? And not a lot of questions. We should speed up.
Right. So yeah, maybe question 13. So the vocabulary update is important when comparing PubMedBERT and BioBERT that are both trained on PubMed. Also, the initial pre-trained model, of course. What role does the server technique like WORD piece play here? Great question. So we actually use the standard WORD piece algorithm to generate vocabulary. Now, keep in mind that BioBERT actually adopt the continual pre-training approach. So it's actually based on the standard BERT. So it actually, by doing that, it is restricted to the standard BERT vocabulary. So there actually the comparison, exactly like you said, like the key difference is actually sort of in the vocabulary. And the subword techniques, so far we haven't tried a whole lot of different variant, and we don't suspect that will be a big difference. But that's a good question.
The next question, 14. Why do you think uncased models generally perform better in bio NLP task? Yeah, I don't know particularly the reason, but the difference between uncased and case in many tasks are not that big. Hoifung, do you have any good answer to this question?
Yeah, I think the sort of the uncase, the advantage for uncase is that your vocabulary actually you can cover sort of a bigger because you basically ignore the case difference, right? Now, intuitively, so some of the bio NLP tasks like entity recognition, right, NER, you feel intuitively the case actually matters. But just like Jianfeng mentioned, like we actually try case and uncase, and we don't see a whole lot of difference. So what we suspect what happened is that even for NER, the context matter a lot more than just the case information, right? So then, and the uncase has the advantage that the vocabulary can capture a lot more, things, because like it basically ignores the case difference.
Okay, next question, 15. Is vocabulary difference the biggest difference between domains, or is it more the linguistics? How do you tease out the difference between the two? It really depends on the model. First of all, I think vocabulary is so far the biggest difference between domains. As for the linguistics, it really depends on what level of linguistics. It's the phrase level, word level, phrase level, sentence level, document level. So far, because all these models do not capture linguistic structures explicitly. So my hypothesis is that even if there's a significant difference in linguistic structure, it may not be reflected in the model. So back to the question, and the answer is yes, given the current model, current study, I think the biggest difference among domains is vocabulary. Thank you. Next one.
Yeah, so the next one is like, can you please give some guidance about making question answering system using biomedical research papers? That's a great question. Frankly, we have think quite a bit about QA for biomed. We are sort of like somewhat sort of uncertain about sort of like how big an impact a QA system. So there are some clear case where the QA seem to be make a lot of sense, right? But also biomedical often is like have such a characteristic where you in each of the specific domain, let's say oncologies or cardiologies and so forth, right? You often know ahead of time sort of like what are the questions. The real challenge is actually finding a lot of the scaling to find a lot of the answer. Like for example, for cancer, like what are the most important genetic mutation and what are the treatment that could potentially target them. So in some sense, like sort of like you have, you know ahead of time what your question often are the most important question, right? So it's more about actually extracting those knowledge and information.
The next question, number 17. How can the NLP extend into clinical practice and applications? I would say so far, the NLP technology, as we demonstrated in the talk and in our paper, is merely playing a role of assistant. They're not going to replace our doctors. I think at this moment, this NLP system is helping to summarize the large amount of documents, identifying key points, and then send a summary of all these key points to the doctor to review, or help doctors identify relevant information from a larger amount of documents or records. So it's mainly an assistant role. Okay.
Yeah, just to echo Jianfeng's point, one thing we think that the biggest sweet spot we can NLP or AI in general can play is like this sort of assisted sort of curation. So normally in any place where you need a lot of human effort to review lots of like for example clinical notes, right? Like a patient could have hundreds of notes, and so the technology can potentially narrow that down to a few candidate places with the candidate answer or information you're looking for. And exactly like Jianfeng said, like we are not imagining like we can get to the accuracy to automate the whole thing, but we can potentially substantially cut down the human manual efforts.
I can probably answer the next one. It's about does it make number 18? Does it make sense sometimes to mask NER? I guess it's name entities, and then continue Pretraining? Yeah, it does make sense. And in some applications, it helps, but we have not run extensive studies, experiments in our paper. And this is related to the so-called span BERT or entity BERT. People already should demonstrate some benefits using this approach in general domain. You want to put
the next. Yeah, the next question is like most of the medical documents are long, and how do you account for representing this large document during language modeling and later using it for downstream tasks? This is a great question. And one thing, as Jianfeng actually alluded to earlier, actually there has been a lot of recent interest in sort of like doing this long range modeling, right? Like expanding the self-attention to a much longer range. It's actually sort of the challenges are actually twofold. One is like we definitely need a lot more of those research into how do we actually represent those large documents, larger contexts. But also for the evaluation, right now I would say a lot of those public available tasks are still relatively focused on the local phenomenon, linguistic phenomenon, right? Oftentimes they may even be a single sentences. So there is probably also a need to actually go to some of those end-to-end scenario to figure out tasks that actually reflect and truly require this kind of bigger context modeling. And in medicine, actually, there are indeed a lot of those use cases. Like in some of our own work, like we look at cross-paragraph, cross-sentence relation extraction. And when you go to a clinical domain, you often have like a patient, you actually need to look at information across different nodes, right? Like not even a single document, like multiple documents. So there is absolutely a lot of need to model a much bigger context, but also one of the bottleneck right now for the research community is the evaluation.
Mm-hmm. So, Hoifung, I think I can take the next three questions. I think number 20. Based on your presentation, is a better approach to build domain-specific models from the scratch rather than adopting general pre-trained models? As we mentioned in the presentation, it really depends. We find that it's beneficial to pre-train model from scratch if the domain is dramatically different from the general domain and there's a large amount of in-domain data. Okay, that is the case of the PubMed. So, next question, 21. Patient-generated information becomes very important in advancing medical practice. Much of this information is on social media. How does your PubMedBERT perform on social media data? Oh, that's an interesting question. We don't have the result yet, but social media data is of a wide variety. So it depends on the task, right? If we define bio-NLP related task on social media data, and the data is very selective for the task, then I bet that the model performs better than the general BERT model. Yeah. Next question. Hi, and question 22. Hi, and thanks for the great event. I am currently a research student and found your work pretty interesting. I was wondering whether I'm able to contribute to any of your projects. Thanks. If you are a student and we have MSI has internship, and you can apply, and feel free to apply online or send email to Hoifung and I. We'll see if there's an opportunity. Thank you. So, Hoifung.
Great. So maybe I would take the next few questions. So was publisher paywalls and IP an issue when working with biomedical NLP domain? So great question. That's absolutely a problem. So in PubMed abstract, you can have access to all 30 million, but for full text, there are only sort of a bulk download portion that currently I think is then about 3 million of them, right? So and there is lots of full text articles that are sort of locked down in the paywalls because of that. So right now we don't, frankly, that's a societal problem or business question. So right now we are mostly focusing on the publicly accessible one. And certainly would be great if we can come to a solution to extend the training and access to beyond the paywalls. There are certainly individual solutions to that. So the next question, what would be approach for continuous improvement of the model with the availability of new research? This is a fantastic question. So it's basically like sort of imagining like you have already trained your language model, right, on 30 million PubMed paper, but frankly, PubMed add 20,000 each week, right? So new papers. So online continual pre-training actually would be actually a very exciting area. We haven't done a whole lot in that area, but there are some obvious strategy to go about that. But this is a great area to look at. Another question, along with PubMed, is there any way we can get the latest live information from doctor treating patient? Frankly, as we alluded to in the earlier of the talk, there are basically a big portion of medical text is from PubMed, right, from the literature. but there is also a lot of information, exactly as I alluded to, come from actually doctor's notes, right? So there is this concept about real-world evidence that we alluded to in the talk. That is become a very exciting area, which is like, what if you can also not only see all the latest consensus knowledge from the literature, and sort of like have this PubMed scale knowledge graph, but also have a population level real-world evidence, like getting all the longitudinal information from patients and so forth. So, and from that, you can actually derive a lot of insight and help prioritize hypotheses and potentially substantially cut down on the drug development costs. So I guess I will take one more, then you will do the 27, Jianfeng?
I can do 27, 28, yeah.
Okay, so let me do the 26 then. Do you have done some analysis on how vocabulary being tokenized? What's the best strategy to evaluate? Good question. So we use the standard word piece algorithm to essentially look at the corpus and find, essentially you can think about this, find the most frequent subset of subwords, right, to best represent the corpus so that you don't have to shatter every word into characters and so forth. So there is frankly a lot more things to be done to compare different vocabulary strategy, especially if you are not, like Jianfeng mentioned, right, like there are not always the case to pre-train from scratch. So if you are in the middle of it, like your what's the best way to like look at the vocabulary? We have some ongoing research, and this is a fascinating area.
So I'll take 27, 28. 27, do you think it's possible to implement NLP to geometric sequence data, like building long word as the sequence of specific protein binding sites? It's a very interesting question, and actually the answer is yes. And I'm sure there are already many ongoing efforts doing this. People start with sequence models for this sequential labeling task. I don't remember specific papers, but I'm sure there are papers already reporting.
Yeah, there are a couple.
Results. Yeah,
there are not a whole lot yet, but there are a couple papers looking at that.
Yeah. And number 28. Oh, it's a bunch of questions. Could you clarify a little bit that it is a base or large-sized model? I think we build both models, base-sized model and a large-sized model. Actually, we made both models publicly available through Hugging Face site, so you can go there and download these two models. Also, what do you think in general domain-specific training? How relevant is a fully domain-specific vocabulary? How relevant is a fully domain-specific vocabulary? And did you meet UNC tokens, for example, using models with not domain-specific vocabulary? I want to clarify, to train models like BERT and other similar models, and the vocabulary is subword vocabulary. So there's no UNC because it's a character sequence. The unit of the character in the extreme case, you think that we can always decompose a word into a sequence of characters, and all these characters, if all these characters are in the vocabulary, so there's no OD in general term. And one more, could you let me know what kind of training method did you use? Oh, everything is standard. We follow the same training procedure as BERT. Maybe Microsoft's Deep Speed solution are a good suggestion, but in this study, we haven't used the Microsoft Deep Speed yet. Cool.
Okay, maybe I can take the next few. Do you plan to include any entity linking tasks in BLURB? Absolutely. There are several kind of sort of like additional data set we are very interested in adding, entity linking definitely being one of them. We are also, like we mentioned a little bit earlier, we are also really interested in finding the tasks that are more sort of like tailored to really end-to-end scenario, and also that often require more sophisticated linguistic, modeling, where you can really start to compare some of those pre-training. Like, for example, one question earlier, people asking about long-range modeling longer context, longer document. You also sort of really need evaluation to actually need that sort of long range. So some of the tasks that people are looking at, like QA or multi-hop QA, and start to actually go in that direction. So absolutely, like the current BLURB version is just the starting point. Based on the next question, based on my biomed research experience, usually uppercase for protein and lowercase for genes, do add this information as a feature as a model. Frankly, like we said earlier, like for NER, right, like the case information intuitively are very relevant. But what we find that is actually the uncase model actually perform roughly the same as the case, actually slightly better. The reason is that on balance, on the uncase, by ignoring the case, you have a more focused vocabulary, and then you still get a lot of information from the context. Frankly, the uppercase for protein, lowercase for gene, actually, as far as I understand, like that's not even true universally, right? Like sometimes it's like uppercase for human genes and a lowercase for mice genes, and so it's a mess, right? So the case is sort of a double-edged sword in some sense, and empirically we find that uncase model actually performs just fine. But you're totally right. Like there is some information there that might be worth digging further. The next question, how PubMedBERT helping current COVID pandemic situation? Actually, Jianfeng and I have active work stream on COVID biomedical search, where we haven't published the result yet, but we have found that actually PubMedBERT substantially outperform a bunch of those standard BERT in a biomedical search. So in the COVID context. So on some of the official evaluation, like track COVID and so forth.
And just want to add that hopefully very soon we're gonna make the PubMed search engine publicly available, which is empowered by PubMedBERT. So probably I can take the next 3 questions. How do the PubMedBERT-based work integrate with the large project handover work, and how can this be extended into clinical trials, matching-based problem? I think you're a better person to answer this question.
Mm-hmm. Yeah. So PubMedBERT really can serve as the basis for a lot of the biomedical NLP. And project handover really sort of focus on sort of like also the application side, right? So as you alluded to, like the clinical trial matching. So a lot of this application, what they fundamentally need is this machine reading capability, right? You need to unlock the knowledge and information, all right? Like you need to unlock the knowledge from the literature. You need to unlock the patient information from the medical record. Now, once you are able to do that, then you can empower a bunch of applications, right? So for drug discovery, for example, they can benefit a lot from PubMed Scale Knowledge Graph. For clinical trial matching, you can benefit from, be able to have, all the detailed patient information from like millions of cancer patients, right? Like in your hospitals and so forth.
Hoifung, I think we should go faster. Let's wrap up.
Okay, sure. Yeah, maybe let me get the next one, and then Jianfeng, you do the next few. Okay. Sometimes some medication are allergic or harmful to a few patients who has other medical history. How to do plan to overcome that challenge when we predict the outcome? Fantastic question. So in fact, this actually touches on a larger theme about real-world evidence, which is like oftentimes when the pharmaceutical company develop a drug, right, and then you start to do clinical trial, you are trying to uncover some of those adverse events that you mentioned about, right? But those trials have limited size, right? Even like large phase 3, like maybe like COVID vaccine, right? That's only like 20,000, 30,000 patients, right? And that's one of the largest one, right? And normal treatment actually often have 3,000, 4,000, and so forth. So you often miss some of those like, rare, allergic events or adverse events. And that's where the promise is that if we can actually unlock all those information from the medical records, right, from the medical history as they were alluded to, but one of the big bottleneck there is actually manual abstraction, manual curation is really not scalable, right? So that's where and actually potential NLP could help scale.
Okay. Next, 34. Following on from the long document discussion, how do you deal with tests larger than 512 tokens during pretraining, or we simply truncate it to 512? Next question, 35. With clean notes, there may be short ends and abbreviations, not proper grammars beyond PubMed. How do we address these problems? Actually, through contextual embedding, we try to link these shorthands and abbreviations to the proper concepts. Yes, through contextual embedding. This is the whole idea of using pre-trained language model. Hoifung, probably can take next two, then we wrap up.
Okay, sure. So how do you systematically evaluate domains that are different? Is there some metric we can use? Great question. So one actual thing that very easy to do is that you can run word piece to generate a vocabulary on different domains, and then you can look at the overlap. You can see that actually general domain compared to PubMedBERT, for example, like the vocabulary overlap could be as low as like 20 to 30%. So that's one metric you can look at. And certainly there are a lot other aspects too. And then next question, like future blur include, it's the same question as asked before, like what about entity linking and other, absolutely. So we definitely are envisioning expanding the blur benchmark. So I think it's time to wrap up. So thank you very much. Thank you all for coming. It's sort of like these are all wonderful questions.
Yeah, thank you. Bye.
Okay, bye everyone. And there was sort of the resource page if you want to sort of follow up and look at later.